Imagine you're moving at the speed of light. Would time still flow the same way? Today, we're beginning our journey into the fascinating world of Einstein's theory of relativity. It's a theory that explores the intriguing relationship between space and time, a concept that has completely transformed our comprehension of physics and indeed the universe itself. It's a big question, a big concept, but don't worry, we're in this together. Intrigued? Good. It's time to delve deeper. Einstein's theory of relativity in a nutshell is all about how we perceive space and time. Let's break this down into its two main components, special relativity and general relativity. Special relativity, proposed by Einstein in 1905, deals with objects moving at a constant speed, specifically the speed of light. It says that the laws of physics are the same for all observers, regardless of their state of motion or rest. So if you're standing still or moving at a constant speed, your perspective of space and time would be the same. Now let's move on to general relativity, Einstein's sequel to his earlier masterpiece. This theory, published in 1916, deals with gravity and acceleration. It's a bit more complex, but in essence it describes gravity not as a force but as a curvature of space and time around massive objects. This brings us to the concept of space-time. Imagine a trampoline. When you place a heavy bowling ball in the middle, it sinks down, creating a curve. This is similar to how space-time works. The bowling ball represents a massive object like a star or a planet, and the curve it creates is the warping of space-time. This warping is what we experience as gravity. So, if you're near a massive object, your perception of space and time would be different from someone further away. It's a bit like being on a merry-go-round. If you're at the center, it seems like you're not moving at all, but if you're at the edge, you feel a strong force pulling you outward. That's the effect of the warping of space-time. But here's the kicker. The more massive the object, the more it warps space-time, and the stronger the gravity. It's like placing a heavier object on the trampoline. It creates a deeper curve. So remember, according to Einstein, space and time are not separate entities but part of a single fabric, space-time. Ever heard of the term time dilation? It's a fascinating consequence of relativity. Let's start by imagining a spaceship hurtling through space, nearing the speed of light. Now picture the astronauts inside going about their daily routines. To them, time seems to pass normally. They eat their meals, exercise, and sleep in what feels like 24-hour cycles. However, if we could observe them from Earth, we'd see a different story unfold. Due to the spaceship's high speed, time aboard the ship seems to slow down relative to time on Earth. This mind-bending phenomenon is known as time dilation. It's a result of Einstein's theory of relativity, which suggests that time and space are interconnected aspects of what's known as the space-time continuum. But why does this happen? Well, Einstein's theory tells us that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source of light. This speed is unimaginably fast, clocking in at approximately 186,000 miles per second. When an object moves close to this speed, strange things begin to happen. For the people on the spaceship, time seems to pass normally. But for us on Earth, their clock ticks slower. This is because the speed of light is a cosmic speed limit, and as you get closer to it, time slows down to keep the speed of light constant for all observers. Think of it this way. If you were to throw a ball in a moving train to you, the ball would seem to travel in a straight line. But to someone outside the train, the ball would appear to travel in a curved path. This is a simple analogy for how relative motion can affect the perception of time and space. The concept of time dilation is not just theoretical. It has been tested and confirmed in numerous experiments. And it even has practical applications in technologies we use today, like GPS satellites. So next time you're running late, just remember, if you could somehow move at the speed of light, you might just make it on time. So why should we care about this theory? It's not like we're zooming around at light speed, right? Well, while we might not be hurtling through space at the speed of light, the theory of relativity does have some pretty significant impacts on our daily lives. First off, let's talk about GPS, or Global Positioning System. These handy little devices that we use to navigate our way around the planet actually rely on the principles of the theory of relativity. You see, GPS satellites are moving at high speeds and are far from the gravitational pull of Earth. This means that time actually runs a tiny bit faster for them than for us here on Earth. If we didn't account for this time difference in the calculations, our GPS systems would be off by about 6 miles a day. That's a lot of wrong turns. Now let's shift gears and talk about black holes. These incredibly dense objects with immense gravitational pull are best understood through the lens of Einstein's theory. Without the theory of relativity, we wouldn't be able to understand the way light bends around a black hole, or how time slows down near one. It's through this theory that we've been able to gain invaluable insights into these fascinating celestial bodies. Finally, let's talk about the Big Bang. This theory, which describes the birth of our universe, is deeply rooted in the theory of relativity. It was Einstein's equations that first predicted a universe that was either expanding or contracting. This laid the groundwork for the Big Bang theory and has shaped our understanding of the cosmos. So, the theory of relativity isn't just about mind-bending physics, it's also about our everyday life. Whether it's guiding us to our destination, helping us comprehend the mysteries of the universe, or shaping our understanding of the cosmos, the theory of relativity has an undeniable impact on our world. We've journeyed through the universe at light speed, warped space-time, and played with time itself. We've explored the key concepts of Einstein's theory of relativity, the unification of space and time, the speed of light as a constant, and the fascinating phenomenon of time dilation. We've seen how this theory has revolutionized our understanding of the universe. Einstein once said, "Imagination is more important than knowledge." So keep imagining, keep questioning, and who knows, you might just come up with the next big theory.